Hello, good afternoon. My name is Wolf, and we are here with the San Jose Astronomical Association for Streaming Solar Sunday. Thank you for tuning in. So yeah, welcome to Streaming Solar Sunday. This is the fourth online solar astronomy event that we're doing, as we are all stuck at home due to the coronavirus crisis. So I'm hoping this is something to, add some entertainment to your Sunday. We did change the format a little bit from the prior events that we've done. The first half, that's starting now, from 1:30 to 3 o'clock. We've titled here Spots, Prominences, Filaments, and More. If you visited this event before in the prior months, this will be more or less the same thing, right? So we will go through all the basics of, these solar features. But then for folks who have listened to this part before and really are just interested in the latest views of the month and some news topics, we've added another segment that will start at 3 o'clock and run through 3:30, and there we'll do topics and views of the month. So so a little bit different today with some new stuff towards the end. So I hope you will all hang around for that. In general, please do give us your feedback via YouTube chat before you leave. It does help us make this better. We are trying to do the best we can for you, and we're learning how to do this. So we really benefit from your feedback about what works for you and maybe what you'd like to see differently in the future. So yeah, think of us before you log out and give us some feedback. All right, and a quick tip for you. We're talking about astronomy. Astronomy is about outer space. Outer space is dark, and you may benefit from turning on YouTube's dark theme for some of the images that we will show. And if you want to try that, you can click on whatever your little avatar icon is at the top right of your YouTube window. If you click on that, you'll pull down this menu. There's the dark theme option in the middle. If you click that, a new menu will pop up with a little slider button on the bottom. And if you click on that one, that should switch you to dark mode. So give that a try if you like. It's entirely optional. Okay, here is the outline for today, the first half of the talk. So we'll do an introduction. We'll talk about how to view the sun safely. We'll talk about the sun's place in our solar system and how we view the sun in different light. Specifically, we'll talk about something called H-alpha astronomy. Then we'll discuss the structure of the sun, share some pretty cool sights, and describe the solar cycle. And as we go through all this, we'll do some visits to the backyard where I have a telescope set up for you guys. And we'll also have some Q&A opportunities in between. Let's quickly introduce the hosts for today. So we have Nancy. Nancy, you could say hello. All right, Nancy's waving, thank you. We have Lipika, who's joined us this week all the way from Austin, Texas. Lipika used to work with us here in San Jose before she moved, but now because of the internet, hey, Texas is just next door, so we're happy to have her back joining us for Solar Sunday today. Then we have Emery online. Cool. And then there's Rashi, who is the master of fruit. You will find out what that means later as we go through the presentation. And then, of course, you guys are stuck with me. So like I said, my name is Wolf. So, all right. Okay. So now we may also meet Zipper the cat. He shares the house with me, and he lets me do stuff every now and then, but he will also insist on making announcements at random times during the day. So if you hear a cat meowing, that will be Zipper, and he is just part of the show. I would like this to be interactive as much as possible. I realize that's difficult over YouTube chat, but let's try. So please do ask questions in YouTube chat as we go along. We will have folks watching this and maybe respond in the chat or hold the question for a joint discussion later. And we'll also have some questions for you where you can participate. So please do that. A quick word about the San Jose Astronomical Association in general before we jump into the detailed content. We are an educational organization and a nonprofit. We offer a whole bunch of public programs, public star parties, nighttime and solar events like this one. We have school star parties where we go out to schools and do nighttime astronomy with the students there. We have public talks and equipment help. So if you have a telescope somewhere in the back of your closet that you haven't used in a decade, we can help you get that going again. We also have swap meet events where you can either sell or acquire some nice equipment. For folks who have chosen to become members, official members of SJ-A, which by the way is only $20 a year, I always say, hey, it's like the price of a pizza, so come on, it's not that much. So if you choose to buy that pizza equivalent, you get to access our imaging workshops. We have training for folks who'd like to get started in astronomy. We have a nice program where you can borrow equipment. We have a library, and we also offer private observing sessions. Now, but of course, because we're all stuck with the coronavirus restrictions. A bunch of these in-person events we cannot hold right now, so we're not doing outside public star parties, but we are trying to bring these things to you, through a medium like this, like we're doing today here via YouTube. And yeah, if you want to find out more, please check us out at sj.net or the meetup group, which is probably how you got here in the first place. And normally, yeah, we are located in San Jose in a place called Hoagie Park. That's our normal base of operations, when things are normal, and we'll get back there, I'm sure. Okay, so yeah, speaking of Hoagie Park, our normal base of operations, so that is normally where we would hold this event. And these are a couple of pictures of past events. You can see there's some tennis courts here, some grass, and a nice sidewalk. So we usually set up our telescopes here on this sidewalk. And yeah, there's a bunch of solar scopes set up that people come by and look through, and then we end up having discussions about whatever interests the visitors. Now, of course, we can't do it quite this way today, right? Because, instead we're sitting here at our computers. But I still want to quickly visit Hoagie Park with you. Whoops, I jumped ahead there. Let me instead click on the button that I wanted to click on, and that will be this one. So here I am showing Hoagie Park through a planetarium application called Stellarium, which is an open source software that you can download yourself if you like. Usually we use this for nighttime astronomy, but I can kind of show you what it would look like if we were in Hoagie Park. Again, here is the tennis court, right, that you saw earlier. And if we look up into the sky, hey, there's the sun. So if we were on the sidewalk, that would be burning onto our heads right now, make us sweat and probably give me sunburn. So, the good news is right now we don't have to be quite that exposed to the bright sun, but this is what we would see. Now, because this is a virtual Hoagie Park, there's a trick we can employ here that is something cool that we cannot do when we're physically in Hoagie Park, and that is I can turn off the atmosphere. So this is what the sky would look like if Earth didn't have atmosphere. Sure, we couldn't breathe, but let's ignore that for the moment, right? Instead, we can kind of marvel at what the sky would look like, right? The atmosphere is what scatters the light from the sun. That's what creates the blue glow. So if we take the atmosphere away, that blue glow also disappears. And then, yeah, you can actually see, otherwise nighttime objects. So, for example, you can tell that, yeah, right here, Mercury is pretty close to the sun. And let's see, and Venus is over here as well. And here is the Orion constellation, Betelgeuse, a very prominent star. These things are usually visible in the winter sky. That's when this is visible to us in the night. But right now, yeah, it's up there in the daytime, which is why we don't think of it as part of the nighttime sky. But yeah, here's Orion's belt. So yeah, this is pretty cool. So we can see, what the sky looks like if we were to turn off the atmosphere. So this is something, we could not do in real life in Hoagie Park. So, all right, but we are not in Hoagie Park. Instead, we are here, and we're using my backyard as a base of operations for today. And this is where, so this is where we have a telescope set up for you today. So you can see it right here. Yep, you can see the leaves blowing in the wind. So this is a live view of the setup that is in my backyard. And we will visit that again in a little bit, and I'll try to show you, what the view through the telescope looks like today. Before we do that, though, I want to make sure we're really clear about how we look at the sun with proper protection, right? Do not look at the sun without proper eye protection. That is really important. So when we do solar astronomy, we don't just take a telescope like you see here on the left. This is the kind of telescope you would use for nighttime work. The opening over here on the left side, that is what we call the aperture. That's where the light enters. Then the light bounces around this tube a little bit and ultimately comes out the back. And that's where you would put your eyeball, right, to see the image through the scope. And we do basically the same thing for solar astronomy, except that, yeah, the sunlight would burn your eyeball to a crisp if we did not employ sun protection. And that protection comes in the form of a solar filter that looks something like this. So it's a plate or a disc that gets stuck to the front of the telescope, and this filter blocks out 99.999% of the light, making it safe to look through the scope. Here's the same kind of thing again, another telescope with this kind of filter attached to the front. And you may wonder, hey, look, it's wrinkled. And yeah, sometimes these filters are made out of just mylar film, so they're actually very thin. They almost look too flimsy to do the job, but they actually work quite well. Glass filters are also available as an alternative. These just offer different trade-offs. But yeah, this is the kind of equipment that you might see, out in Hoagie Park on the sidewalk if you were to come visit. These kind of filters are available also. Okay, one second. Yep, Rashi wanted to add something. What you got, Rashi?
Yeah, sorry about that. I know you're just getting to it right now, but just be
Hmm.
mindful that when you're using these filters, that you're not putting the filters on the back end,
Hmm.
scope or between your eyes and the binoculars, because that light will still destroy the filters, melt the filters, and still hurt your eyes. So they need to be on the primary lenses, in front of the telescope or the binoculars.
Correct, yeah. And I'm sorry, I think I accidentally hit the wrong button while Rashi was talking, so you may missed a sentence or two. So Rashi was saying that, yeah, notice that in these pictures, the filters are on the front of the telescope, not on the back. There are different solutions here. I'm not showing all the possibilities, but yeah, most of the solutions do put the filter on the front, and that's exactly where it needs to be. So yeah, thanks, Rashi. Okay. All right, and yeah, these kinds of filters are available also for binoculars. So here you can see the same kind of thing bolted to binoculars. So that can be kind of a cool way to look at the sun. And then, of course, you may have seen these kinds of uh, solar glasses. These were all over the place during 2017 when the solar eclipse was happening, and we'll need them again in 2024 when there'll be another solar eclipse. So yeah, so in this picture you can see a whole bunch of students looking at the sun, and they all have their glasses on, except for this girl who smartly is not looking at the sun because I guess she forgot her glasses. So yes, please always use proper eye protection when you look at the sun. It's very important because you will be blinded if you don't do so. Okay, so now with that safety announcement out of the way, let's talk about the sun in its place in the solar system. So this is kind of a cool picture. Here's the sun in the middle. It's really big, and then you can see representations of the planetary orbits around it. So here's Mercury, Venus, here's the Earth with our moon, and then Mars, then there is the asteroid belt here, and then the other big planets, Jupiter, Saturn, Uranus, and Neptune. And yeah, so this is a really nice picture, but in some ways this picture is completely wrong because it does not accurately represent the scale of our solar system. And scale is actually really hard to show. This next picture attempts to show the scale, but yeah, notice that the slide is mostly black because space is mostly empty. There's just lots of nothing in between things. So you can see a sliver over here on the left, that is the sun. Then you can see a few tiny dots over here. These tiny dots are the inner planets, and I think Mercury is so small that you don't even see it. But the Earth would be, the Earth would be here, and then this guy here is Mars. Here's the asteroid belt, and then you can see the other planets again. Pretty spread out, right? Notice how close to the sun the inner planets are, up to Mars, including the Earth, and then how spread out things get after that. So yeah, so this gives you a little better idea of how things are really arranged in the solar system and the spacings of our major solar system objects. Okay, now let's ask a question. How do we see stuff? How do we see anything? And of course, the answer is light, right? Right now, you're looking at a computer screen and you can see it because there are light emitters in your display, that are going through some color filters, and that ultimately allows the monitor to uh, present a color image to your eyes. If you look out the window, right, you can see trees maybe because the sun is emitting light and that light is bouncing off the trees and then going to your eyes. So yeah, light allows us to see, but let's think about that light a little bit more. So here's a couple pictures of rainbows. I took these pictures, I don't know, over the course of the last year or two because I like rainbows. I just think they're really cool. And I'm sure you've all seen them, right? And rainbows are natural phenomena that split the white light from the sun into its color components. And you've probably also seen the same effect when you take a prism, right? You run white light, a beam of white light through a prism. The prism will split that white light into the rainbow. It's the same basic effect as you get with a rainbow in the sky. Now, if we get a little more sciencey about this, it looks something like this. So really, light is just a tiny portion of this whole thing that we call the electromagnetic spectrum. There are lots of types of radiation, and radiation often sounds like a scary word, but actually it shouldn't really be. Yes, there are scary parts of radiation, but on the whole, we're bathed in radiation all the time, and it's perfectly fine. And in fact, we rely on it for lots and lots of things. Sunlight or visible light is a type of radiation that our eyes can detect, right? So we have evolved detectors for this really narrow range of the entire electromagnetic radiation spectrum. But then we've built instruments to see other parts. For example, down here you can see AM and FM radio. And yeah, you may have detectors for this in your house. You may have a radio you can turn on and you can sense, the radiation that comes in these forms. Microwave, yep, that happens in your microwave oven. Also your Wi-Fi router is doing its thing somewhere in this range, right? It's also a type of a radio. And then, yeah, we have got the infrared light here. Infrared light is what you feel as heat. So if you hold your hand up to the sky outside and your palm feels warm, it's because, yeah, your hand is sensing the infrared radiation coming to you from the sun. Then here's the stuff that we can see. Ultraviolet light is the part that gives us sunburn, especially me. I need to be careful outside, and so should you. And then X-rays, you're familiar, of course, from the doctor's office. And then there's something called gamma rays out here that are very energetic. And these things are pretty dangerous. But luckily, we don't really have to deal with these on a regular basis. They may come from outer space, but it's infrequent. And for the most part, our atmosphere can help us shield out these things that are dangerous to us. So, but yeah, this is the entire electromagnetic spectrum. And our eyeballs can only detect this little sliver right here. Okay, armed with that information, let's look at this poster. So this is something that we usually have out in the park, and we use this as a discussion starter, so I want to use it here today as well. Now, there's a lot going on here, so we'll kind of step through this one by one. First, let's look at this thing here on the left side. You see this yellow image of the sun, and it's labeled photosphere. The photosphere is the term we use for the surface of the sun. Now, the sun does not have a hard surface like the Earth, but there is effectively something like a surface. So the photosphere is it, and this is essentially the part that emits all the light that we see. And the photosphere may have features called sunspots. We'll talk about this a little bit more as we go through the rest of the presentation, but you can see some little examples of it here in this picture. If we move away from the sun a little bit, we leave the photosphere and we will enter a region called the chromosphere. And in this region, we find features called prominences and filaments in something called the H-alpha view, and we'll describe more what that is. So we're going to be talking about this a whole bunch more today. And you can see that this view has some different structures in it. It provides some different details. It shows different features than the prior photosphere view. And the similar thing happens if we move over here to the inner corona. Again, we've taken another step away from the sun, moving farther out into essentially the sun's atmosphere. And there, again, you can see slightly different features. Now, this is not a view that we can get here from the ground, because like I said earlier, our atmosphere will actually shield out some of the higher frequency radiation. So this ultraviolet light that is emitted by the inner corona, we cannot see from the surface of the Earth. We have to send the spacecraft out beyond our atmosphere. The final picture here is showing the outer corona. And the outer corona is this stuff that extends way out here from the sun. You can see it going out in all directions. The outer corona is generally only visible during a total solar eclipse. So the picture that's shown here is kind of a cheat, actually, right? The corona picture was taken during an eclipse, and then an image of the sun was, again, superimposed on top of it, so you could kind of see what the sun looks like in context. But you would never actually see this combination in reality. You can only see the corona if the sun is obscured by the moon during an eclipse. But yeah, so the corona extends out very, very far, right? It's a pretty amazing structure, and it's beautiful to see during a solar eclipse. Okay, on this slide, it's just another example of what we talked about a moment ago. I mentioned that, yeah, depending on what light we use to look at the sun, we see different features. And so I don't really want to talk about all these in detail, but it's just to illustrate that, yeah, that's kind of how science is done. We use different instruments that allow us to see the sun in light our eyes cannot detect. And yeah, that reveals different details and allows us to study different aspects of the sun. So each one of these is a different slice of the electromagnetic spectrum, a different type of radiation, and they all provide some different information that's important for studying the sun. All right, and so at this point, let's take a short break and see if any questions popped up so far.
No, we don't have any questions at all in the feed.
Oh, wow. Okay. Maybe people are making it too easy on us, but okay, we'll go along with that for the moment. But maybe we can ask a question to our audience, right? And so, yeah, you see this cool picture of this game wheel, and hey, look, Nancy has one just like it sitting next to her. So she's going to give this a spin, and this is going to give us a question that I would like you to help us answer. So, Nancy, you want to give it a whirl?
Yes, thank you. Thank you for the presentation.
So, Nancy, we're all going to win $1 million, right?
That's right. And a new car.
Oh my God,
let's do a couple questions. Okay, first one. Okay, we have B category. Let's see. What's the B question? Okay. All right. So what particles does the sun produce that are passing through your body right now?
Oh, that's a cool question. I love this question. All right. Okay.
Pretty cool question, huh?
Yeah.
I'll do one more question, let you think about it. And once you have the answer, please post. And here comes second question. Let me see. Where's I? Okay. Okay. So for the I category, yep, I got that. The parts of the sun above the photosphere are collectively known as what?
Oh, okay. So that one should be an easy one if
Okay.
you guys were paying attention. Okay, so.
I know. I think
Yeah.
you just say something like that, something in that neighborhood.
Exactly.
So
right?
let me
This is a
repeat.
good quiz question to see if our audience is awake.
Yeah. Okay, so the first question, what particles does the sun produce that are passing through your body right now? Second question, the parts of the sun above the photosphere are collectively known as what?
Okay. Okay. We need some music like from Jeopardy, like do 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 do.
Yeah.
Right?
Yeah.
Are
Any
we getting
taker?
any takers for this one? At least for the second one. Come on, guys.
No, not yet.
That's easy.
I'm disappointed. You guys are all fired, but that's fine. Okay, we'll move on, and we'll give the answers away, I guess, right? So, Nancy- are we getting something? Oh,
yeah, we've got
okay. I'm
Marianne.
jumping the gun. Good
and
thing I
one
didn't say
neutrino.
that. Okay.
Ding, 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 ding.
All right. Marianne to
Q1
the
or question one
rescue.
neutrinos by Marianne.
Yep.
Correct. Yeah.
That's absolutely right.
So neutrinos
then-
are some really cool particles, and maybe we should have a separate talk just about neutrinos someday, right? But this is something. It's probably a particle that most folks have never heard of, right? You may have heard of, atoms have, of course, protons and neutrons and electrons, and that's all good. But there are additional particles that are zipping around out there, and one type is a neutrino, and the sun actually emits a whole bunch of neutrinos. They are almost massless. They are no charge, so they don't really interact with much, and they just flow mostly through everything that they encounter, including your body. So I always forget these numbers, but I think the number is like about 1 trillion neutrinos per second are passing through your body right now, and you're not feeling any of them. So I find that kind of an amazing little fact. So,
Yeah, it's roughly 100 trillion.
100 trillion. See, I'm bad with numbers,
Yeah.
so thanks for fixing that up for me.
I wonder how many of those pass through us at night.
Oh, that's a good question. I think the answer
Good
is
question.
probably about the same, right? Because they will also pass mostly through the Earth. There actually are neutrino detectors that we've built, and they are built like deep underground. I think the way these are done is like giant pools of water deep underground to shield from other types of radiation. And then every now and then a neutrino will bump into something and generate some other type of radiation that we can detect. But most neutrinos will just zip right through the Earth. Some get, interact with something because the Earth is pretty big. But yeah, most will actually just go right through too, I think.
Awesome.
Very
And
cool.
Steve just gave the answer for the second question on the chat, chromosphere.
Awesome. Thank you. Okay, you guys are rehired. Thanks. I appreciate that.
Yes.
All right. Okay, moving on. Let's see. So, okay. So we talked about the light a moment ago, right? So here's a picture of the sun up in the sky. Probably looks a lot like that right now if you were to look up. And we said the sun is what gives you the view of the photosphere, right? The photosphere is essentially the part of the sun that emits the light, and if we just wear proper protection or put filters in our telescopes, we can then see images like this. But the chromosphere view requires that we go back to the sciencey stuff here and we think about what's happening in the electromagnetic spectrum. So let's talk about that for a moment here. So we all know that the moon is made of cheese. This is common knowledge, right? So that's pretty clear. But then what is the sun made of, right? And it turns out the sun is made out of one of these things on the periodic table. And you've probably all seen this at one point, maybe back in high school, who knows? But yeah, so there is this thing up here, hydrogen, right? That's the simplest element on the periodic table, and the sun is mostly that. And so the sun is hot hydrogen, right? So hydrogen is very energized up there, and it's forced to glow. And let's see, so how does hydrogen actually glow? And if we go back to the original full rainbow down here and then ask how hydrogen glows, it turns out hydrogen glows in some very specific colors. Hydrogen will glow in this purplish color here that's at a wavelength of 410 nanometers. It will also produce this blue color at 434, and then this one at 486 nanometers, and then this thing we call hydrogen alpha light. So remember we talked about hydrogen alpha briefly before. So there's this thing called hydrogen alpha light at 656 nanometer wavelength in the red. And so yeah, so hot hydrogen gas emits just these four colors in these very precise positions within the visible range. Now, outside the visible range, there's actually lots of other contributions that hydrogen makes, but within the part that we can see with our own eyes, we get those. And the one that we're most interested in for today is this hydrogen alpha line. Just for comparison, here are similar what we call spectral lines for other elements. So helium has this other pattern of bright lines, and oxygen and carbon, and each element on the periodic table has a very unique pattern, which results in some really cool science that we can do, because we can look out into distant space, look at the light that we see from something, and we can tell what it's made of by analyzing this barcode, essentially. It's a lot like a barcode at the supermarket. You scan it and whoop, you know what kind of stuff is at the other end. But again, today we're mostly looking at hydrogen, and we care mostly about this hydrogen alpha line over here. So we have special solar telescopes that include precision filters that specifically isolate this hydrogen alpha light, right? The one that we mentioned before. And an example is this telescope right here. This was made by a company called Lunt, and it's called an LS100 because the opening here is a 100 millimeter aperture. So the light enters here, goes to the telescope, shoots out the other end, but along the light path is actually a different kind of filter than what I showed at the beginning. So here, you know, there are these funny cylinders sticking out. If you're curious what those are, you can ask in the chat. But the short version of the story is that these filters are these cylinders are part of the filter mechanism that is built into the telescope. So light enters, fancy equipment inside isolates the hydrogen alpha spectral line, and then we can look just at that color. Here's a smaller version of this, just as a point of interest, right? This is the same type of idea. Again, it's got one of these funny cylinders, and there's a built-in filter. This is a 50 millimeter version, so it has a smaller aperture over here. And the cool thing is that if you are an SJA member, you can actually borrow one of these through the loaner program, and here's that loaner kit. So, hey, this is pretty cool. It's an incentive to join SJA if you want to try your own hydrogen alpha solar astronomy at home. As a second option, there are also hydrogen alpha telescopes from a company called Coronado. At the top is something called the Personal Solar Telescope, or PST. This is probably the least expensive telescope of this kind you can buy. Here's a little bigger one on the bottom. And it actually turns out that very soon SJA will offer a PST also in the loaner program. So one of these is coming. So that will be fun. But then, yeah, today, again, we're using a Lunt 100 that's sitting in my backyard. It's something called double stacked. It has to do with the filters. If you're curious, ask in the chat. But then, yeah, we're not there to put our eyes on the eyepiece today, right? Because you're all sitting at your computer. So how do we get the image to you over the computer? And we do that with the camera. So instead of the eyepiece, we have actually this kind of a camera stuck in there. And you can kind of see in here is the sensor. So the camera sensor is, yeah, it's kind of tucked away in there. And so earlier we saw this view from the poster. This was this chromosphere view that was taken in H-alpha light by NASA. And then just as a comparison, down here is a picture I took in 2017 with the type of setup that I was just describing with those telescopes from the prior slides. And, you know, it doesn't look quite as fancy because this was a really quick snapshot, but yeah, you can definitely see there's some stuff going on here, you know. And so prepared with that background information, let's go back and visit my backyard one more time here. So here's our telescope. Let me find my window. Okay, so now we don't really want to look at the telescope anymore. Instead, we want to look here. Haha. So this is a live view through the telescope with the kind of camera that I showed a moment ago. And we will have our crew join us as well, so they can add information if they like. So yeah, and you can see this is what's going on right now. You may notice that the image is jiggling a little bit, and that's because of atmospheric disturbance. So there's heat rising from the ground that actually causes the air to be unstable, and as a result, the image is dancing a little bit. It's just something that we have to put up with when we do this kind of work.
Oh my gosh, Wolf!
Yeah,
That looks like this orange that I have here.
There
I
you
mean, the
go. It
texture
does,
on
right?
the orange
Yes.
is exactly like what you're seeing on the scope there.
Exactly. Yeah. So often, actually, yeah, we describe the sun's chromosphere texture kind of orange-like, and you can see it, right? This is not smooth in here. There are kind of light and dark dimply things, I guess, right? And that is real texture. Again, it may appear a little wavy or kind of jumpy because of the atmospheric disturbance, but nevertheless, this is real structure within the chromosphere. And we can play with the camera controls a little bit, to perhaps change what detail and what features we see. Notice there is something here that looks like a scratch or a scar. These things are called filaments, and we'll describe more what that is in a moment. But so this is an interesting feature here. Here's another one of those things right there. And hey, look, there's a little thing sticking actually out from the sun. So we call that a prominence. That's a tiny one. But hey, there's something going on over here. Let's see if we can zoom in on that a little bit. So let me go back.
You're absolutely right. Mr. Orange is making a visit from the orchard right now.
Oh, there you go. That's I find that amusing and also quite slightly unsettling. So thanks, Mr. Orange. So let's see. Yeah. So if we so I'm moving a telescope right now with these remote controls, and yeah, check this out. Right. So down here there's something erupting from the edge of the sun. You kind of see this poof, right, that's sticking out. Now, this may not look all that big, but keep in mind that the Earth is actually pretty small compared to the sun. We could fit 109 Earths across the entire sun diameter. So the Earth is smaller than this poof that you see here, right? And this poof is hydrogen gas, hydrogen plasma erupting from the outer layer of the sun, driven by strong magnetic fields. And we'll talk about that a bunch more as we go through the rest of the day. But yeah, so it seems like today we actually have some interesting features to share, which is nice. Okay, let me go back into the presentation material. That will tell you a little more about what we're seeing, and then we will revisit this live image again. Okay, actually, before we do that, that's right, let's take a quick break for questions one more time, right? Just in case some questions popped up in the context of, the hydrogen alpha telescopes or anything like that. Our audience seems to be making it too easy on us. And Rashi already gave away what kind of cheese the moon is made of. Okay, so that's not going to be a question.
Yep. Sorry, Swiss cheese.
All right, should we give the wheel another spin then? Let's see. If we're not getting any questions, then we can make some questions.
That's right. We'll go. We're going to ask you some questions.
I'm rooting for a Tesla this time.
Is that?
So I'm rooting for a Tesla. Go for it.
Oh, rooting for a Tesla. Okay.
Okay, we have Jay coming up. All right. So, okay, what would become of the sun when it runs out of fuel and dies? That's question number one. Okay. One more question.
Yep.
Okay. And is H. How does the sun produce energy? I like this question.
Okay, that's a good question too. Yeah. The wheel would have been better if the wheel had come up with these questions in the other order, but that's okay. The wheel does what it wants.
Yeah. So the first question was, what will become of the sun when it runs out of fuel and dies? Mm-hmm. Second question is how does the sun produce energy?
Yeah. So today, of course, the sun is producing energy. We feel it as heat and see it as light. And that's been going on for a long, long time, and it's going to keep going on for a long time, but it will not go on forever, right? Yeah. So however the sun is making energy today, that will not last. At some point, it will run out of whatever it's doing up there, and our sun will die. And then what happens to that? All right. Do we need the Jeopardy music again?
All right. Question 2 by answer by Steve. Fusion.
Okay. Yeah, okay, right. So the sun generates energy through fusion, nuclear fusion, right? So the sun is a giant nuclear reactor of sorts where, we said earlier, the sun is made mostly of hydrogen gas, right? Hydrogen. And in the core of the sun, that hydrogen gets smashed together and undergoes nuclear fusion. The hydrogen fuses together to produce helium, the kind of stuff that you find in party balloons. And it turns out that fusion process generates huge amounts of energy that then, like I said, we feel as heat and see as light. So, yeah.
What about the first question? Any taker? What will become
yet.
of the sun?
Well, yeah, because
Not
the hydrogen
yet.
won't last forever, right? So again, don't worry, it's not going to run out tomorrow. We got plenty of time, right? The sun's been doing this for about 4.5 billion years, and it's going to keep going for about that much more. But eventually, the hydrogen will be largely consumed. And then what are we going to do?
We do have an answer from Marianne. It will puff up, it become a red giant, then it will become a white dwarf.
Yeah, right. So stars go through life cycles. Thanks, Marianne. Right. So yeah. So eventually, our sun will actually swell. It'll become larger and larger, right? And that's when it goes into its red giant phase. And when it starts to do that, it will appear larger and larger in the sky, and eventually it will, I think, possibly even bump into the orbit of the Earth. We won't be here anymore at that point. We'll have moved out by then, let's say. But yeah, and after that, the sun will puff out its outer layers. It kind of will blow a giant cloud of material out into space. It's not exactly an explosion, but it kind of poofs it out. And then in the center, there'll be left something called a white dwarf, which is inert material, mostly carbon and oxygen, that will be hot for a long, long time, but it will no longer be producing fusion energy. So yeah, that is in our distant, distant future. And the cool thing is, if you visit nighttime star parties, you can look at objects in the night sky that have already done this, right? So you can see the kind of thing that our sun will turn into by looking at parts in space where this has already happened. So I encourage you to check that out. So, all right, thank you.
Yes.
All right. Let's see, moving on. Okay, so speaking of, the sun and it poofing up and all that, there's a quick video here in terms of size comparison. I think this is pretty cool. Because, yeah, I said earlier that our Earth is pretty small compared to the sun, and this little video gives you a much better feel for the relative sizes of things. And it is pretty amazing, I think. So, yeah, so here's our moon, and if we go from there, Mercury is a bigger object, and then Mars is there, and then we get to Venus. Venus is pretty close in size to Earth, actually, right? It's a little smaller, but you can see the Earth next for comparison. Now, then from the Earth, we'll take a big step up to Neptune. These are now the gas giants, right? Neptune being the first one. There's Saturn. And then Jupiter, which is the largest object in our solar system other than the sun. And boom, here's our sun, right? Pretty big. But just in case you thought our sun was big, well, it's not nearly the biggest kid on the block. Here's a star called Sirius, then a star called Pollux. And notice, by the way, the Earth has long disappeared in the bottom of the video, right? So now we're looking at Arcturus. That's a star that's actually up in the night sky right now. Aldebaran. And I'm starting to lose our sun down there, right? It's become pretty much too small to see. Here's a thing called a Pistol star. Look at how big these things are. Antares, that's also a star that's visible right now in the night sky. Yeah. So, I find this video just mind-blowing, right? Think about how large things are out there. Right. So, so our Earth is pretty big. It would take us a long time to walk around it. Our sun is very large compared to the Earth. But there are stars out there that are just so much bigger than the Earth. And if you were to take some of those stars and plop them where the sun is, yeah, the Earth would be inside them, no problem. Okay. Oops, we already did the answers. I'm sorry. I messed up my own flow, but that's okay. Hey, this is live TV, folks. All right, moving on. Let's talk about the structure of the sun a little bit more. This goes back to one of the questions that we actually had a moment ago when we talked about, what is producing energy in the sun. And so let's talk about the structure that goes with that answer. So inside, the core of the sun, that's where the nuclear reaction happens. That's where the nuclear furnace is. This is where hydrogen is fused into helium and the energy comes from. But moving out from this layer, we go through this thing labeled number 2, which is the radiation zone. And this is kind of a cool region, actually. Cool as in interesting. Because what happens is that energy will be produced in the core. So a photon, a particle of light or an energy, will zip out of the core and it will enter the radiation zone. And it turns out it will take thousands to possibly millions of years for that little photon to make it through the radiation layer. And the reason this happens is that this photon takes essentially a random walk. So the photon zips across the 1 to 2 boundary, and it will almost immediately run into a hydrogen atom, let's say, right? It'll run into something, that hydrogen atom will absorb it and then re-emit the photon in a different direction. So the photon comes out and then bounces off in a different direction. And then this will keep happening. So it'll be this zigzaggy random walk. And eventually, just by luck, that photon will make it to the 2-3 boundary and be able to leave the radiation zone. So this random walk, yeah, it can take variable amounts of time, thousands to millions of years.
And Wolf, one thing to add there is for people that want to visualize it, they can visualize it as a pinball machine, right? So you've got that ball that's bouncing around and just keeps on bouncing until it finally gets a chance to exit.
Yeah, I like that. Thanks. That's another good analogy. I agree. Yeah. So it essentially is kind of a random bounce, right? It'll go crazy for quite a while there, possibly until it finally makes it out. Thanks. And yeah, so then once we made it through the radiation zone, we entered this third layer, which is called the convection zone. That is a zone where energy is transferred largely by boiling. It's the same kind of thing that would happen in a pot on your stove if you, let's say, boiling noodles or something, right? In the noodle pot, yeah, you'll see water bubbling up in different regions, right, from the bottom, and energy is transferred by the water circulating in your pot. And the same type of thing is happening in the convection zone, and we'll talk about that a little bit more shortly. But once we make it through the convection zone, then, yep, we're at the photosphere. We talked about that before. That's where the light is generated that then is emitted out and we get to see it. And so, yeah, while it took a photon maybe 1,000 to 1,000,000 years to get through the radiation layer, once it leaves the sun to get to us, boom, they only got 8 minutes to go, right? So the light speed distance from the sun to the Earth is about 8 1/3 minutes. Pretty fast at that point. Beyond the photosphere, we have the chromosphere. We talked about that. It's like the innermost layer of the solar atmosphere. There's a lot of rarefied hydrogen there. Then we go out to the corona that we've mentioned before. We mentioned sunspots before, right? These are structures that appear within the photosphere. We'll see a little more of that in a moment. And then there are these things called, granules. These are essentially the convection regions, right? The different boiling regions, and we'll see more of that also. And then prominences. So prominence here is like this loop. Here it's illustrated like this loop. And this is hydrogen plasma, charged hydrogen gas that is following magnetic field lines. And yeah, we saw a little bit of that just a moment ago in our live view even. Okay, so let's talk about sunspots a little bit more. So yeah, we get those in what we call the white light view. So at the very beginning when I showed you telescopes with a solar filter on the front, that kind of setup would be fantastic for looking at sunspots. Turns out that right now the sun is not really offering us any sunspots to see, and I'll explain later why that is. So this is a picture from past years. But here we had really nice sunspots. Yeah, you can see like this really big guy and lots of other ones nearby. And here's more or less the same picture with the Earth for comparison. Yeah, so sunspots can be huge. They can be the size of, let's say, a major city here on Earth, or they can be big enough to swallow up the entire Earth. And in fact, back in, I think it was 2014, there was a sunspot that was so big that you could see it with the unaided eye. I mean, you had to wear your eye protection, but you did not need a telescope or binoculars. You could just look at the sun wearing your solar protection glasses. And yeah, that was a big enough sunspot that you could just see it that way. So that was pretty amazing. Here's a close-up view.
On it. There you have your own personal dark spot.
Okay, here's an orange with a dark spot. There's a sunspot on a fruit. As I told you at the beginning, Rashi's our fruit master. Now you know what that means. So. Okay, so and here's this close-up view of a sunspot, right? So you can see there's this dark region here. And actually, this is a little misleading. It looks dark, it looks black, right? But actually, it's still really hot and bright. Just relatively speaking, it is not as luminous as the region around it, so it appears dark to us. But it is actually still quite hot and bright. It's just a relative appearance. But yeah, there are these cool, fantastic structures kind of reaching out from the sunspot. These are all these different kind of boiling regions. And yeah, speaking of boiling regions, right? So this is a close-up image that was taken earlier this year. I think this was from February. This is pretty new science. So this is a very high-resolution picture of the photosphere. And yeah, each one of these little granules here is essentially a boiling region like you would see in your noodle pot. So this is just a really amazing picture, I think. And I'll ask you a question here. Do you like miso soup? I do. So, when I wasn't stuck at home all the time, I would sometimes go to Japanese restaurants. And one day I was looking at the miso soup and going, hey, you know what? This looks a lot like what's happening on the sun. Because, so here, right, you see kind of the miso is rising up, right, because the soup is hot and the miso kind of comes up and then circles around. That's the kind of convection action that's also driving the sun. And so next time, look closely at the hot soup in your bowl, and you can do some mental solar science, right there. And so we just looked at the miso soup in action. And so here again is the miso soup of the sun. So let me show you a video of that, because I think this is pretty nice. Where are we? Here we go. Okay, so here's an animation of this, right? So this was, again, taken by or distributed in February as New Science, and you can see actually a time lapse of this boiling or convection action on the outer layer of the sun there on the photosphere. So pretty neat, I think. Okay. And just to put this into context, so the big square image I showed you in the prior slide, that was this part of the sun right here. And then if we zoom into this further, again, you see these detailed convection regions. And look, here's Texas for comparison. So Lipika lives somewhere in here. She would live somewhere in one of these tiny spots. Okay, so we just talked about the photosphere and the sunspots we see there. And then if we move out a little bit into the chromosphere, right, the first atmospheric layer, that's where we see this orange skin texture again that we mentioned earlier. And you can see these features around the edge of the sun. And also, again, here's some of these scars or scratches that I mentioned earlier. Right? And here's a slightly closer view of some of this stuff. And here you can really see well what's happening. So here again is one of these eruptions, and especially this one is cool because you can really see the three-dimensional structure of it. So like we said before, strong magnetic fields are driving hydrogen plasma away from the sun, and in this case it's creating almost like this shark fin or blade-like structure. And you can see that this structure sticks out from the edge but also continues into the disk of the sun. So it turns out that these scratches or scars that we see, which are actually called filaments, are essentially the same thing as this stuff on the side, which we call prominences. So a prominence and a filament are really the same type of thing, but we see them differently, right? It's a different perspective. So we call them a prominence when they're on the edge, and we call them a filament when they're here, but they are the same type of thing. They're a three-dimensional eruption, right, that's reaching out from the sun. Strong magnetic fields driving hydrogen plasma. Here's again the picture that I showed earlier, my quickie picture from 2017, and now maybe you can see a little better what's going on. So this W shape is one of these big filaments, and you can kind of see this is raised, right? It's three-dimensional, it's sticking out from the sun, and here is a prominence right there. Right? And so with this, maybe we'll take another quick look at the backyard and see what's happening there. And so now you can maybe appreciate a little better what's happening here. Let's see, let me get the telescope control. Okay, let's see, let's focus just a little more on just this guy here. And so what I'll do is I'll increase the exposure a little bit so that will make the disk of the sun brighter, but it will also highlight that prominence a little bit more. So the prominences come in all kinds of shapes, partly dependent on our perspective, from what angle we're watching, and also driven by what the magnetic fields are doing on a particular day. So there's this nice poof of material that's sticking out here. And again, the Earth is pretty small compared to this, so this could engulf the Earth. Okay, let's take another quick sweep. Sure, go ahead, Roshi. What you got?
I was just going to say, it seems like the sun forgot to shave today. You got one single strand sticking out right there.
Actually, if you look, you're right. I mean, sometimes the sun is in terrible shape, right? It's got whiskers all over the place. But actually, up here you can see it's pretty smooth. There's a little, I don't know, I see like a little dimple here and here, but that's almost too tiny to really talk about. But up there it's pretty smooth. Let's see, but let's turn the exposure back a little bit. So note you can see, this is kind of cool, right? Here you can see some structure within the disk of the sun, right? So here again, these shapes are largely driven by magnetic fields that are pulling the hydrogen plasma in one way or the other. And like we said earlier, down here, it looks like there's some small filaments. So these are really 3D structures that are sticking out, towards us.
Yeah, and one of the reasons why I always bring an orange to the session is because this becomes a great aid, right? Especially if you are walking children through or explaining things to them, orange becomes a great aid to explain, the surface of the sun, even dark spots, or even filaments. You might have scratches on the surface of the orange itself, and you can use that as an example.
Yep. Yeah. And so right here, there's like a little prominence, right? There's a little bit of a proof here. Go ahead, Nancy.
Hey, Wolf.
Yep.
So I just have a question. Something like what we just saw, that whisker that Rashi was referring to. Aside of that, how long do you think it lasts before it dissipates? Is there a way to
good. I don't know if how long does it last before it goes away, right? I don't have a good answer for that particular structure, but I think in general, prominences will last for hours to days. I mean, they do change, right? Because things are moving. And in fact, I'll show you some cool time lapses of this kind of stuff in a moment. But yeah, prominence will be there, changing over time a little bit, but be there for hours to days. And sometimes when we are sitting out on the sidewalk in Hoagie Park, we start the event at 2 o'clock typically, and it ends at 4. And sometimes over that course of the 2 hours, we can see actually some change in those structures. Now, it's two things. It's the the prominence itself changing, and it's also that the sun is rotating. So both of those things are causing changes in perspective. But point is, yeah, we can actually detect changes in these structures, and how they appear to us, sometimes even over the course of one afternoon event. But they will
I guess it reminds me of the last time that we were doing the presentation. We started with a prominence, but then through the course of the presentation, it did go away.
Yeah, right. So I think there are multiple things happening actually. So yes, sometimes things actually get worse, unfortunately, right? Sometimes we start out with a pretty nice prominence showing up at the beginning of the event, and then an hour later it's like, whoops, where did it go? And a few different things will have happened there, right? It's not necessarily that the prominence itself disappeared, although it could have actually changed on its own. But like Rasi's showing, the sun actually rotates, right? So the prominence may have rotated, out of view or just changed angle, so we can't see it so well. Also, unfortunately, right now, my telescope is sitting in the backyard and I cannot keep tuning it. The fact that it's hot out there changes actually, heat causes things to expand and the like, right? So in Hoagie Park, I'd be tweaking the filters and the focus as we go through the 2 hours. Here, I cannot do that. So part of the problem also is that the telescope settings will drift a little bit from the ideals. And then finally, there is just, atmospheric disturbance. That can change, right? So how noisy the atmosphere is and how much it degrades the view can change over the course of an afternoon. And that can also, unfortunately, sometimes ruin the image. We get what we get. Okay, cool. All right. Let's go back here. And let me show you some pictures of fantastic prominences from past years. So look at this thing, right? So this is, of course, way bigger than what we are getting right now in our real-time view. So this is, quite spectacular prominence. You can see there's a lot of activity here on the sun. And here is a video that I want to show you that I referred to a moment ago. This is a nice time lapse of a prominence forming and then kind of disintegrating, and it's just a beautiful video. So you can see this was back in 2012, so it's about 8 years ago. All right, so here, of course, is the sun as it's seen by the equipment that we have out in space. And now we're going to be zooming in on a region where all the excitement will happen. So you can see there's something going on already, right? There's definitely a bright region, so there's something of high energy there. And something is now developing, right? You can see that there is an arc forming, so magnetic fields are pulling hydrogen plasma up from the sun. And it's growing. So again, this is a time lapse. It does not happen this quickly in real time. But so you see the loop forming. And you can already see, this becomes more prominent in a second here, but you can already see that material is kind of dripping down, right? So gravity of the sun pulls the material back. Magnetic fields are pulling it up, and then gravity is pulling it back down, creating this what they call fiery rain. So this is just a beautiful, spectacular image in my mind. And you can see the Earth there for scale, right? So pew, you could shoot the Earth, or even a much bigger planet, right through that loop. So I just think this is quite beautiful. Oh, Rashi's asking whether Jupiter could make it through the loop, and I think Jupiter was a little too big for that one, right? I think shoot, I should know this off the top of my head, but like I said, I'm bad with numbers. That's always my excuse, right? How many Earths fit across Jupiter? 12, something like that. That's probably
something like that. I don't remember.
Yeah, something like that, right? So I think Jupiter might have been a tight squeeze for that one, but we can certainly get these structures that are big enough to shoot Jupiter through as well.
Wow.
Yeah, and so here we have some views of prominences from total eclipses, right? So this was from 1999. So this is actually quite fantastic. So if you have not seen a total eclipse yourself, hey, go check it out in 2024. Normally we need our hydrogen alpha telescopes to isolate the hydrogen alpha light, that red light, right, that reveals the prominences. But during a total solar eclipse, you can see them with out those special filters. You still need to have your eyes safely protected, of course, but when the disk of the sun is blocked, all that bright light that usually just blinds us from everything else is hidden, and then these details around the edge just pop into view. And so these prominences here were visible without special hydrogen alpha filters during a total eclipse. So it's just really nice. Here, this is from 2017. This is actually a picture I took. I got lucky. This was an iPhone picture at the eyepiece of my telescope. I wasn't even trying that hard, and I just got lucky. The moon is just moving out of the sun, so this is just as the total eclipse is ending. So that's why you can see this bright sliver of light here, right? So the sun is starting to reappear, but it's still not bright enough that it's washing out this prominence that's sticking out. And when I looked at the telescope to see this feature, I was kind of unprepared for it. This just kind of blew me away. It was just really amazing to see the prominences so distinctly without a hydrogen alpha telescope. So I highly recommend you checking this out. And here's another total eclipse, and look at this prominence, right? Here the prominence is huge. It's almost like a handle on a bowling ball or something, right? It looks like this big handle. And not only is this a cool prominence during a cool solar eclipse, where you can also see again the corona, reaching out into space. But notice this was from 1919. So this picture is historic for a key reason, that it was used to help demonstrate that Einstein's theory of relativity really works, because the theory of relativity predicts that the gravity of the sun or other highly massive objects will bend light around them. And so this solar eclipse was used to demonstrate that fact. And every test that we have thrown at the theory of relativity since then has held up. So Einstein has been doing quite well since he came up with that stuff. So here's a few more prominences. Again, this is just amazing, this big thing reaching out into space. Here's one of those giant loops, right? Here we can probably fit Jupiter through it. Pew, no problem, I think, right? And here's another really amazing, huge arc. And let's see, we actually have a video of that kind of a thing happening, so let's run that. So as you can see, a lot of these videos I've pilfered from NASA, right? So these are the things you can look at yourself if you like. They're available on YouTube or on the NASA site. And it's amazing, what our technology and our instrumentation allows us to reveal about, in this case, the sun. So again, you can see the loop forming, and in this case it's actually ejected out into space, right? The prior picture we saw, the prior video of the looping rain, gravity was pulling the material back down to the sun, but sometimes the event is so energetic that stuff is actually ejected out into space, and that's what's happening here. So here's, I think, the same thing just one more time from the perspective of the whole sun. Boom, right? Spitting this out into space. So very energetic events. Okay, we can take another quick question break. Did anything pop up in the chat?
No, we don't have any comments or questions that have come up. I mean, of course, appreciation for some of the images, and of course, some association with food. But otherwise, nothing else.
All right. Okay, shall we give the wheel another spin then? See if we get any interesting questions from our circular assistant?
Yeah, sounds good. So I think the fact that there isn't any question, I think Wolf did a good job just explaining all the details associated with the topic. So he covered everything. Let's take a look.
Or we're all in food coma.
Or was in food coma? Yeah, maybe it was too close to lunch. I don't know.
So, category F. Okay, let's take a look.
And if
Okay,
it's a Tesla, we'll have to email it to you, and you can print it out or something.
that's right. This is something pretty close to what you mentioned just now. How many Jupiters would fit across the diameter of a sun?
Oh, okay. There you go. All right.
Okay, so we just mentioned that. Funny how
Kind of, yeah. And actually, I'm not even sure of the exact answer because I always forget these details. So in a moment, we will get the right answer.
Okay, and that's I. Okay, let's see. For that, okay, the question is, what is a solar filament?
Okay, so that one too. If you were paying attention, you should know this one. So dig deep in your memory, about 5 minutes back, and you may have the answer.
So let me repeat. First question
okay, please.
Is how many Jupiters would fit across the diameter of the sun? Second question is, what is a solar filament?
Cool. All right. And while folks think about that, let's see. So we can just show another little video here. Let's see, where did it go? So it just pulls together some of the stuff we've been talking about, right? So while you guys are thinking about those questions and are popping your answers into the YouTube chat, here's a video of just cool surface action, or chromosphere action on the sun. So yeah, different kinds of prominences, right? So you can get material erupting from the sun in different shapes, again, all driven by magnetic fields of different types or different sizes, strengths, and shapes. And notice these are all images in different light, right? So some appear yellow, some appear reddish. These are all images taken by instruments, mostly through light that we actually cannot see directly with our eyes, right? But we see it with technology, and then we remap it to colors that we can see. So here's a lot going on, right? You can definitely see that there are structures that seem to look like magnetic field lines. A topic we'll talk about a little bit more in a moment. So yeah, kind of cool stuff. Okay, so let's see. Did we...
So Steve says for question 2, a prominence looking edge on.
Okay. Yeah, exactly. So we said a filament is the same as a prominence, right? But it's we're kind of seeing it in the disk of the sun. So that's why I refer to them often like they look like scratches or scars. So yeah, thanks. Cool. Okay.
What about the other question? How many Jupiters would fit across the diameter of the sun? Any taker? Any guess?
Not yet.
What do you think, Rashi? Wolf?
Shall we give it a countdown? Tick tick 3, tick tick 2, 1.5, 1.25, 1. All right, Nancy, all yours.
Okay. It's about 10. The answer is about 10.
10.
About 10 Jupiters can fit across the diameter of the sun.
Okay, so I'll make sure my brain remembers that for next time. So thank you. Okay, cool. All right, let's go ahead and move on here, and let's talk about the solar cycle. So, excuse me. Turns out that the sun has weather. Well, in fact, we've seen examples of this weather, right? So you could describe some filaments and prominences, some of the eruptions that we've seen as like solar storms, if you will, right? So the sun has changing conditions, just like we have changing atmospheric conditions here on Earth. So there is a type of solar weather, and that weather goes through a major cycle, just like we have our seasons here on Earth, right? So we kind of have a yearly cycle where we go through spring, summer, fall, and winter. Something sort of like that happens on the sun as well, with its own cycle. And here's an illustration of this from the past. So there's a cycle that started in 1996, and the representation here, you can see in the back, the sun looks, relatively boring, right? It looks kind of uniform, not a lot going on, a couple bright spots here, but on the whole, not so much. But then as we move towards the front, as we go through the years, in 2001, you can see that the sun has a lot more going on, right? There's a lot more bright regions, meaning there's some energetic action going on. And then this diminishes again as we go through back to 2006, which completes the cycle. And so the solar cycle is an 11-year thing, right? So while we have seasons that iterate every year, the solar cycle is an 11-year cycle. And let's kind of see what's going on there, right? Here's a different representation of this. So solar cycle 22 was the one from like 85 to 97. Solar cycle 23 is roughly what we just saw, I think, on the prior slide. And we just completed solar cycle 24. The curve that you're seeing here, and a lot of wiggly lines, oops, sorry, my finger slipped. So the wiggly line you're seeing here is the sunspot count. So all the time, NASA counts the number of sunspots on the sun. And the number of sunspots is an indicator of how active the sun is, right? So how many dark freckles you get, little ones, big ones, indicates how active the sun is. And so the wiggly line is the actual sunspot count. And then this is averaged, and that gives you this smooth line that you see kind of going through the middle here. Okay, and so the last solar cycle started around, here, 2010-ish, okay? And then look where we are right now. We are here 2020, and this line is basically hitting a minimum. We're almost at zero again, right, for sunspots. And so that's why I couldn't show you sunspots today, because there aren't any, right? So the sunspots are far and few between at this point in the solar cycle. Back in 2014, when I mentioned I saw this giant sunspot on the sun that I could see just by wearing eye protection without any magnification. Yeah, that happened right here during the peak time, right? That's when the last solar cycle was at its peak of activity. So unfortunately we're right here right now, so that makes it a little hard for us to find exciting features on the sun. But still, today actually the sun offered us some kind of fun stuff to see. But so what's happening here is that it's all about magnetism, right? So the sun is mostly hydrogen plasma, like we said. Hydrogen plasma is essentially hydrogen atoms that have had their electrons ripped from their nuclei. And so it's really a tremendous soup of protons, which are positively charged, and electrons that are negatively charged. And charged soup is moving around partly through convection, like we said earlier, right? So the boiling action moves the soup around, and the soup also moves because of another thing called differential rotation of the sun. So the boiling we talked about already. Let's quickly visit this rotation idea. So here is a diagram of the sun that kind of illustrates how it rotates around its own axis. So just like the Earth, the Earth is spinning around an axis, and for us, one rotation is pretty much one day. No matter where you are on the Earth, it takes one day for the Earth to make a revolution around its axis. The sun is a little more interesting in that regard. The sun is, like we said at the beginning, it doesn't have a solid surface, right? It's basically a sloshy ball of hydrogen. And so it turns out the rotation rates are different depending on where you are on the sun, what your latitude is. So right near the pole, turns out if you were to stand right here, you couldn't really stand there, but just imagine for a moment, if you stood right here, it would take you about 35 days to make one whole loop around, one revolution around the pole. But if you were on the equator, hey, look, the equator actually spins faster, right? So turns out if you stood here, it would take you only 25 days to revolve all the way around. So yeah, it turns out that the rotation speed is not uniform across the latitude along the sun. It actually varies. And so this is what we call differential rotation. And the impact that has is as follows. So imagine for a moment that we hit the reset button, right? And everything starts out nice and smooth. But now the equatorial region actually rotates faster. And so as things rotate, you can see that, the equatorial region is getting dragged along faster than everything else, right? So near the equator, near the pole here, things rotate slowly. Near the equator, they rotate faster. And so as time progresses, this gets dragged more and more to the point where over here, it gets all twisted up, right? And this twisting is part of what causes all the interesting magnetic activity, right? Because the charged soup that makes up the sun is being twisted in this way. And as we move and twist magnetic soup, if you will, right, charged soup, then the magnetism becomes very complex, and that creates the solar activity essentially. And that gives us our 11-year cycle, because here things are pretty clean, right? It looks kind of like it does over here. Then we go through, we kind of reach maximum messiness around the peak of the solar cycle, and then it turns out over time it essentially unwinds itself and kind of repeats this cycle. So it's all about magnetism, like we said, right? So you've probably seen pictures like this, north south. This could be like a simple bar magnet, like you might have used in science experiments in school. And you've probably seen pictures like this where the magnetic field lines are drawn. And here is a bar magnet where it's like hidden under a piece of paper, and magnetic iron filings were put on top. And if you kind of tap that, turns out the iron filings will arrange themselves along the magnetic field lines. So this is representation, a real physical representation of this diagram. And so this is what magnetic field lines look like when we play with the bar magnet. And the same kind of thing is happening on the sun, because moving charge creates very magnetic fields. The magnetic fields can in turn affect the motion of the charged soup. And all this interaction, right, can then slowly, can locally slow the convection, causing sunspots, right? So we said the outer layer of the sun is this convection zone where things are boiling, but if we have strong magnetic fields, they can stop or suppress the boiling, and then you get a locally cooler region that becomes a sunspot. And also, again, these strong magnetic fields can drive the prominences and solar flares and things like that. Here's a representation of magnetic fields on the sun. So, you've probably all seen a picture of the Earth with the Earth's magnetic field. It's very orderly, North Pole, South Pole. It's very boring, relatively speaking, which is good for us because we can use something like a compass to help us find north. But the sun is much more messy with regard to its magnetic fields. So here is a representation of the magnetic fields of the sun on March 12th, 2016. So a bunch of measurements were taken, and then computer models were run that extrapolated these magnetic field lines. And you can see it's a big mess, right? It's like you woke up in the morning and you forgot to comb your hair, especially now with pandemic hair, right? This is very much kind of a messy organization. And you can see that on a different day, there's a different messy organization, right? So here is the same type of picture, but from a couple of years later. And every day this changes some, right? So the magnetic details and fields on the sun, they vary all the time, and they are what are driving the overall solar cycle. And on a given day, they give us different sunspots and different prominences and filaments. And with that, let's see. Should we take another moment for questions?
Before we get into that,
Please.
a couple of comments I'd like to
Yes,
make. So the differential rotation that you talked about can also be seen with our outer planets. So you can see that with Jupiter or Saturn. You can see that how the equatorial regions move faster than going closer to the poles. That also causes a little bit of more of a bulge in the center, as opposed to when you're reaching out to the polar regions. So you can definitely see that.
Yeah, it's an interesting point about it. So actually, it turns out that so all these celestial objects that are rotating around the axes, they're actually not spheres, right? Even the Earth is not a sphere. We know for sure the Earth isn't flat, so let's get that out of the way, right? But then we said, oh great, the Earth is a sphere. It's like, well, that's more true than the Earth being flat, but actually it's also not perfectly true, because actually the Earth is a squished sphere, and that is because it is spinning around its axis. So all things that spin around their axes essentially are a little fatter around the waist, and they're kind of squished spheres. So the sun does this, the Earth does this. But yeah, good point. So the outer gas planets, right? Because they have in some ways a structure more like the sun, right? The Earth is rocky, the sun is a gas blob, the outer planets are gas blobs, right? So yeah, so there you can see the differential rotation as well.
Yeah, and one other thing to call out regarding the solar cycles, the solar cycles are not from the time that the sun formed. It's when we started actually recording solar cycles. So that started in roughly, I think, about 1755 or so. So now we are in the 25th solar cycle.
Yeah, good point. Right. So yeah, thank you, Rashi. That's a good clarification. Right. On the diagram I showed, they were labeled like 21, 22, 23. But yes, the sun has been around for way more solar cycles than that. It's just when we started realizing this was going on and we started labeling them. So yeah, good point.
Okay, I have a question.
Okay.
Wolf. Okay. So regarding the solar cycle, you were talking about magnetic fields and how it relates to sunspots. Is there a way to predict sunspot at this point, according to scientists, or is it just day in and day out observation?
Good question. So I don't know if I have a really authoritative answer for this, right? I mean, we are doing solar signs in part to help us predict what happens, and we'll actually talk about that a little bit more, when we get into the news segment today, because yeah, solar weather is actually very important to us. I mean, one is just cool to look at through telescopes, but it turns out in really extreme cases, what happens on the sun can really have a strong impact here on the Earth. Day-to-day impacts might be how pronounced the northern or southern lights are, right? Which I've never seen. One of these days I have to go see them. I want to go see the aurora, right? Some of you may have had a chance to see it before. I don't know. But yeah, so how strong, how active the sun is on a given day would affect our northern lights. If the sun is emitting one of those huge blasts of material that we saw earlier in one of the videos, then we could be in trouble if that actually hits the Earth, right? So if it goes off into empty space, which it does most of the time, who cares? But if just by chance it shoots off in the direction of the Earth, we would be impacted. And something like this actually happened, and I always forget the date. There was something called the Carrington event back when telegraphs were the technology of the day, when the internet was just the telegraph wire. But there was a really powerful solar eruption, and it hit the Earth. And this event actually energized the telegraph network. It induced electricity. I think it caused some injuries. And imagine if that happened today. Today, our technology relies so much more on electrical things, right, than were in use back in the telegraph area. So now, if we had a powerful solar event hit the Earth, boy, we could be in trouble. And that's one reason why we have, science that's studying the sun and trying to figure out how these things work. So that's kind of a long-winded answer to say I don't know, but that's why it's important, and that's why, scientists actually do study this and do try to make predictions about these things and trying to figure out how to predict these things better. Yeah.
The Carrington event was end of August, beginning September of 1859.
Thank you. Okay. I know you've told me this once before during this exact same event, right? But I always forget. Thanks.
No worries.
Okay. Well, if nobody else is asking us questions, we can spin a couple more times and see if a Tesla comes up, or otherwise we'll just get a question. So.
That's right. Let's go for a Tesla. H. Okay, H comes up a few times today. Okay, so here's a question for H. Is any of the radiation emitted by the sun harmful to us? If so, what? Okay, question number 2, second one. I. Okay. Oh, this is a good one. What causes auroras?
Oh, okay.
Okay. So
it's like
let me repeat the question.
We're just talking about, right? It's like
Yeah. So let me repeat the questions. Is any of the radiations emitted by the sun harmful to us? If so, what? And then the second question is, what causes auroras?
Yeah, okay. All right, guys, so help me out here. See if you can give us some answers. At least for the second one, I think I kind of gave it away a moment ago. Although, actually, we didn't talk about it in that much detail for the aurora. So, yeah. Please give it a shot and answer that for us in the chat. And while you think about it, let's see, we can visit the live view one more time. So let's see what's happening in the backyard. All right, so yeah, okay, so here's that prominence we saw earlier. You may notice that when we started, it appeared more like over here, and now it seems to have moved, and that's an artifact of how the telescope is tracking the sky. So that is not something that the sun is doing. That's something that essentially our telescope setup is doing.
Yeah, I gave our folks on question 2 a couple of choices.
Okay.
4 choices to pick from.
Thank you. That sounds good. Okay, let's see. Oops, wrong button. Although, hey, there you go. Yep, that's the. So by the way, yeah. So the telescope is sitting on a mount, right? You can see, here's the telescope tube, the Lund 100 I showed in the slides earlier. This camera is sticking where the eyepiece would normally be. This is where we would put our heads if we were to look through it directly. Now there's a camera with the cable that goes to a laptop that's sitting in the backyard. And the whole thing is sitting on a mount that is computer driven, and it's actually tracking the sun. So as the sun is moving across the sky, the mount is moving, and it's slowly repointing the telescope to keep it aligned to the sun. So that's how we're able to talk here and go back to it and, hey, still see something. Because if you have a telescope that is not tracking, the object that you're looking at will actually move out of the telescope very quickly within a matter of seconds. The sun would have disappeared if the telescope were not automatically chasing our current target of the sun. Okay,
and Wolf, maybe later on it'll be good for you to add 1 or 2 points on why your camera is not getting fried.
Okay, sure. I mean, the short answer is that our eyes would be safe, right? Because the camera is sitting in the same place where our eyeballs would be. So at that point where the camera is plugged into the telescope, it is sitting after all the filters that make it safe for us to view with our own eyes. But yeah, that goes back to what we said earlier at the beginning, right? You do need to have proper protection on your eyeballs and on binoculars. And if you want to try to take pictures of the sun, you need to have proper filters there too, because your sensors will be destroyed if you don't have any filters in front of your camera, right? If you try to take pictures of the sun with, let's say, your DSLR or something like that. So your sensors would be destroyed just like your eyeballs would be. So, but in this case, yep, the camera is benefiting from all the same filters that our eyes would benefit from. So let's see. Yeah, again, I think here is we have, yeah, again, the filament is here. So again, keep in mind, this is three-dimensional. It's sticking out towards us, actually. You can still see the orange skin texture. And actually, if you look at it really closely, I don't know how well this is coming through on the YouTube stream, but if you look at it really closely, there are moments when things seem to be slightly better in focus, and the orange skin texture looks a little crisper, a little more clear. And yeah, that is a lucky moment while the atmosphere is otherwise causing the image to kind of wiggle a little bit and wash out. Yeah, but we still have our prominence down here. And yeah, if we turn up the exposure, then the disk of the sun becomes brighter. But you know, we can see the filament, excuse me, the prominence a little bit better down here. Oops, and why am I clicking on the wrong button? There we go.
All right, Steve's answered the question too. Atomic particles from the sun.
Okay.
For the auroras.
Okay. Yeah, exactly. So atomic particles from the sun, essentially the kind of a solar wind, right? So the sun actually constantly blasts out protons and electrons, essentially the parts of hydrogen nuclei off into space, right? So there are charged particles coming towards us all the time, just like there are neutrinos coming towards us all the time. Except while the neutrinos go through the Earth, through us, the charged particles are actually intercepted by the magnetic field of the Earth, and they are rerouted such that they ultimately cause the northern and southern lights. So yeah, that's cool stuff. Has anybody actually seen them? I'm curious. If you're in the chat and you've seen the aurora, chime in and let me know. Then I can be properly jealous of you. So don't miss that opportunity. So.
Nancy has.
Do you have? Oh, okay, I'm jealous of you. Wah.
It was actually a trip. I went to Alaska,
Mm-hmm.
and it was like 2 o'clock in the morning. It's just beautiful.
Yeah.
Something I've never seen before. So it's totally worth it. If you have never seen it before, you need to take a trip somewhere where you can see the auroras.
Yeah, see, I make myself feel a little happy by turning on the lights that are northern facing in my apartment.
Yeah, I think that's gonna have to do it for me too for now, right? Until we can go visit Alaska again.
Okay.
So, all right, let's see. So what else do we have then?
No one's answered question 1 yet.
Okay, I actually forgot. What is question 1? I can't remember now. Oh, radiation of the sun, right? Was it dangerous? I don't know. What do you guys
Is it
think?
harmful to us? No?
Yeah.
Any guess? Henry?
Okay, so while people are guessing, here, I'll show another video, I guess, here, right? Just to give folks a little more time to think about that. So here, this is based on another video that NASA just published very recently. And so this really illustrates nicely what's happened over the last solar cycle and why today we're having a hard time finding, exciting details on the sun. So here, this is 2010. So this was, around the beginning of the last solar cycle, and you can see that there's some stuff going on, right? You can definitely see some of this magnetic activity on the edges. You can see there are these bright regions, right, where there is energetic activity. So back in June of 2010, there would have been some interesting things to see through a white light telescope looking for sunspots, or certainly through an H-alpha scope like we're using today. Now we switch gears to October 2014. Look at how much more active the sun is, right? So there's so much more going on. It's really obvious that there are just way more magnetic fields driving, rearrangement of plasma. And actually here is this giant sunspots. You can see it in the corner, and the rotation matches the image below. So this, I think, is that giant sunspot that I saw, that I described earlier, or that you could see just with the unaided eye. So that's October 2014, and now we are in May 2020. So that's now, basically, and look how smooth the sun is, right? So here, it's just like this fuzzy, cuddly ball, basically, compared to that really energetic thing that was creating all those cool sunspots back in 2014. So every now and then we do get something interesting, like that little loop that you see right now, and like the prominence we can see in the real view today. But yeah, right now the sun is pretty quiet, right? And that's why we're having a hard time finding really big structures like we would have had back in 2014. So the sun does what it does, and so every time we look at the sun, we just hope there's something interesting on a given day. But we will be heading back towards a new solar max, and we'll see more interesting features in the future. Okay.
Yeah, and many folks
answered.
Many folks talk about the solar cycle as a heartbeat of the sun.
Thanks. Yeah.
So that's another way to look at it.
Yeah, and to go back to answering the question for number one, well, the first thing I thought of was like, okay, we apply sunscreen to protect ourselves from something. So that would be the sun, and so UV radiation.
Absolutely, right? Yeah, and especially I need this, right? I will burn super easily. If you stick me out in the sun for 15 minutes without sunscreen, I'll be bright red. That's bad. It hurts. I've had some really bad sunburns, and it was pretty slow learning that lesson. But these days, yes, I put on sunscreen to go outside because some of the UV radiation is dangerous to us, right? It can cause skin cancer, for example, right? And some of us are better adapted to bright sunlight than others, right? Partly a function of our skin pigmentation. But so UV light is something we need to be very conscious of. Yeah.
Yeah, and Marianne's answered as well on the chat with gamma rays disrupting DNA, X-rays can cause cancer, UV sunburn, IR heat burns, microwave cellular disruption, ultrasound can cause cavitation, and of course the big question of how do we ever survive?
Yeah, that kind of goes back to the idea is like, the universe in many ways is very inhospitable to us, right? I mean, we enjoy our nice place here on Earth, Bay Area and even Austin, Texas. Not so bad, right? But there are lots of places in the universe that are actually quite inhospitable to life. So we are, quite lucky to be here. Although it's really the flip side. We are here because this place happens to be hospitable to life, right? So we can look at it that way.
Yeah, and then she also answered her own question. We are protected by our atmosphere and our wits and knowledge.
Yeah, exactly. So the atmosphere is a really big deal. I mean, you've probably all heard about the ozone layer, right? That was a big deal in the 70s, I guess, right? Use of certain propellants for spray cans and stuff, right? It turns out they would react with something called ozone. That's a type of oxygen that's in the outer layers of our atmosphere. And turns out ozone is key for filtering out UV light. And those chemicals were eating a hole into the ozone layer. And turns out that's actually repaired itself to some extent. But it's still there. And we need to be conscious of these things, right? Because we can do things that inadvertently affect, how protected we are from outer space.
And I think they were, chlorofluorocarbons, right? If I remember right.
Yeah, isn't it another thing that protects us, Jupiter and its moons, to block craters? I think that's another way that we get protected.
Good point. Yeah, that's not from excuse me, not so much from radiation, but certain large objects, right? May be intercepted by Jupiter, right? So we don't get smacked and have another event like the one that killed the dinosaurs. Although that too could in principle happen, right? So just like there are folks watching the sun and learn to predict dangerous events there, we also have astronomers looking for asteroids, right? There are programs, missions, right, that catalog asteroids to help us detect something that could potentially hit the Earth and cause an event like the one that killed the dinosaurs. And if we detect that early enough, we even have some ideas for how we might protect ourselves. So it's cool stuff. Okay, let's see. We can take another quick look at the backyard, I guess. So in 2 minutes, we're making the official transition to the second part of today, which will be the news. And that's where Nancy, Lipika, and Emery will share their news items for the day. But before we start that, let's visit the backyard one more time here and give folks who are dialing in specifically for 3 o'clock a moment to connect. Let's see. Can the Rashi, can your son smile? Does that work? Oh, it kind of works. Okay, there you go. So we were joking earlier that for when we get close to Halloween time, right? Maybe we should have a special online astronomy session, either daytime or nighttime, where we will all be in disguise of sorts. We can have a Halloween themed event. Let's see. Okay. Yeah, like I said earlier, keep in mind, if you are an SJ member or if you want to become one, you can, through the loaner program, check out Hydrogen Alpha Scope, right? That can help you get these kinds of images from your own backyard. So that's a cool thing you might want to entertain. Okay, and with that, let's introduce ourselves again quickly for the second part of this show. So some of you might have just joined us. My name is Wolf, and I'm here with my crew for the day. And this is now the second part of our streaming Solar Sunday. And during this half hour between now and 3:30, we're going to focus just on some live views of the sun. If you have not seen what the sun looks like today, we'll show you that. And we have a few short news items. So this is a new segment that we're trying. You can let us know whether you like this or not, and that can help us decide how to run these events for the future. So, but yeah, here we are, streaming Solar Sunday with topics and views of the month. So we can, again, for those of you who just joined us, let me quickly show you what's happening in my backyard. So as I do every time for these online Solar Sundays, I have a telescope set up in the backyard, right? It's sitting on this mount that is automatically tracking the sun as the sun is going across the sky. And there's a telescope stuck in the back, a camera, the blue camera stuck in the back of the telescope where the eyepiece would normally be. And that allows us to get a view like this. Oops, come on. There we go. So this is the live view through that telescope with the blue camera in the back. So here's the sun, and you can see, we have our orange skin texture of the chromosphere. You can see that the image is wiggling a little bit, right? That's atmospheric disturbance. Let's zoom around a little bit here, or pan around a little bit and see what we get. And we know that we had something interesting near the bottom, so let's go and check that out. So yeah, let me turn up the exposure a little bit to bring out the faint features. Yeah, so this is what we've got today. So the sun is offering us a pretty nice prominence. Actually, I think this is something bigger than we've seen during the prior month's events. So here is a prominence where there's a pretty nice eruption kind of arcing over this way. So that's pretty cool. And there are also I had some filaments here. Yeah, you can see actually right here. So here is a filament feature. Yeah, it's a little fainter than it was earlier, but so here's a filament. So this is also a three-dimensional structure where hydrogen plasma is erupting from the sun. Essentially the same thing as a prominence, but it's just in the disk of the sun towards us. We can quickly look at the images I captured when we started. So here, yeah, this was when we started today, just before we went online. This is a picture of that same prominence that you just saw on the bottom. So yeah, this is what we had earlier, maybe a couple hours ago. You could see the prominence here, and nice texture within the chromosphere. And yeah, here's the same thing, just exposed a little more strongly. So this is where, wrong way, excuse me. So here we have the disk of the sun, of course, very brightly exposed, but that makes it easier to see the prominence that we had here. So yeah, this is from a couple hours ago. And then I think the other capture I have here is something, yeah, so that kind of shows, again, the other side. Right, and yeah, there's a little bit of a prominence here, right? And yeah, again, here's that filament that we saw. Okay, yeah, so that's kind of what's happening on the sun right now. So we'll go visit that again in a little bit. But given that introduction to today's sun, let's go ahead and jump into our news topics for the day. So Nancy will start us off talking about the solar orbiter.
Thank you, Wolf. So recently, the European Space Agency, or the ESA, along with NASA, announced that the solar orbiter spacecraft spotted previously unknown campfires on the sun. We're going to take a look at that today. So just a quick acknowledgement, all the information I'm sharing with you are pulled from ESA and NASA websites. So credit goes to them. And also, there's so much information about this mission. And I invite you to check out their website for more, to learn more. A little bit about the timeline of the mission. The mission was scheduled to launch in July 2017. It got pushed back multiple times, and it was finally launched in February 10th, 2020, just 6 months ago, at Cape Canaveral Air Force Station in Florida. 2 days into launching, the solar orbiter deployed instrument and antenna to communicate with Earth. At the end of May, it captured the first images of the sun. Around the same time, it also passed through tails of the comet Atlas. By mid-July,
so this is not the comet that we just saw, right? Just that was a,
no.
a different comet, right? Just
comet,
to be clear, right? Yeah.
Yeah. This is comet Atlas.
Yeah.
Okay. So in mid-July, around 2 weeks ago, ESA and NASA formally announced and released the first set of images that also include some of the images have campfires. And we'll get to see those shortly. And as of today, the spacecraft really hasn't officially started its science phase of the mission, yet it has already producing some pretty mind-blowing results. And this mission is going to last into the year 2030. Okay, so at this point, I'm going to take a look at the first image with you. This is the image of the many phases of the sun. It was taken by some remote sensing instruments on board. If you look at the top row, the yellow suns, along with the right, far right, orange ones, as well as the middle one, the right center, those are captured by the same remote sensing instrument at different wavelengths. The yellow ones were captured at 17 nanometers, and the orange one, the orange-red one, will capture at around, I believe, 30 nanometers.
Yeah, so this is all stuff we cannot see, right? These are all
correct.
Types of light that our eyes cannot see. We just need instruments, right, to see them?
Yeah, absolutely. Yeah. Absolutely. So, and then I'm going to, let's take a look at the left column middle image. That white image there, it really shows the magnetic map of the sun. The white and the dark regions, it really translates into the opposite magnetic polarities. Bottom left, the colorful one, is the line of sight velocity of the sun. The blue is turning towards us, and the red's turning away.
Oh, so this is cool. Yeah. So this is like a Doppler image, I guess, right?
It's actually a tachogram, yeah.
And okay. Actually, I don't know what that word means even. What say that word again?
You know what? I'm going to have to explore some more on that. That is just directly copied. I haven't got a chance to research too much on that. It's something we can talk about later.
Yeah, that's actually really cool. I mean, maybe just, if you don't mind, I'll add something quickly to this, because, I mean, yeah, it sounds like it's even the blue and red seem to make sense in the context of Doppler shift, right? And it's something we didn't talk about during the first half of today. But, when something moves towards you, like you've all experienced this if you're standing at the side of the road and there's like a car with the horn blaring driving past you, right? You'll first hear the pitch of the horn elevated, and then once it drives past you, all of a sudden the tone or the pitch is lower, right? So it's like, right? And turns out light does the same thing, right? So when something's moving towards you, the light is actually shifted towards higher frequencies, towards the blue. And when it's moving away, it's shifted towards lower frequencies, the red. So I think that's why I was asking if this is like a Doppler type image. And so yeah, this is really cool, actually. So I did not.
Yeah, actually, I took a glance at it, but with the time slot that I'm given, I basically have to go through.
Sure, I understand, right? I just thought it was.
And no, good question. Actually, maybe a good topic to bring up one of these days. Okay, and then the last one, the lower center, that smooth-looking one, much better than Rashi's orange.
Very smooth.
He's got texture. Mine doesn't have any texture. That really shows the visible light image of. That's what we would see with the naked eye. Okay, so let's
like
go to the next
photosynthesis.
image. And
Okay.
yeah, the next image, I'm going to show you some campfires. Right there. So I want to get you familiarize yourself with the campfires in these images. I have them in little circles. Actually, highlight that. Hopefully, you can see that. And these campfires, you'll be able to spot them in the next in the video clip that's coming up. Please.
Okay.
The video, please.
Yeah. So here we go.
Okay, so you can see there are campfires everywhere, the little ones. They're so tiny. These images were captured at 48 million miles away from the sun, so it's quite close.
Yeah. And so in comparison, how far away are we on the Earth now, actually, right? Just to put that into context.
We're about 94 million from
93,
Earth
yeah.
to sun. That's the distance. So this is about roughly half.
Halfway, yeah. Okay.
Yeah. So these campfires, they're believed to be 1 million or even 1 billion times smaller than the flare that we see from Earth. They're everywhere. So scientists really wondering if these campfires are just the really small version of the big flares, or are they driven by different mechanisms? Okay, and there are theories that campfires could be the contributing factor to extreme temperature at the corona.
Yeah, very cool. Right? So this is detail we didn't even know existed, right? So this is so we had to get halfway from here to the sun to see this at all. So I think this is very cool.
Right. So they're tiny little ones. The term campfire, it took scientists a little while just to come up with how to name them. You know, they come up with like micro flare and mini flare, but they finally settled with campfires. So that's going to continue. But so the purpose of this exploration is to answer some big questions. They're very mysterious questions, some of them, such as what happened in the polar regions, something that we don't know much about. Question about solar wind, we still don't know everything, magnetic fields, and space weather, okay? And the spacecrafts will go outside of the ecliptic plane and climb to higher latitudes where it will be able to study more about the poles. So in order to do that, its orbital path will remain in sync with Venus so that it can take advantage of the gravity assist flybys of both Earth and Venus to change the trajectory and climb above the ecliptic. With that,
and
it will
the ecliptic being, just
the,
make sure we're clear about the ecliptic being basically the plane of all the planets, right? So you have the sun here and you have the planets orbiting around the sun. And essentially that plane of the solar system is essentially the ecliptic, right? So you're saying the spacecraft will climb above that, right? Yeah.
Correct. So the ecliptic pretty much, basically the rotational plane of the planets. By doing so, it will change the trajectories of the spacecraft. It'll be able to climb above the ecliptic and guiding it toward the innermost region of the solar system, so we can get more detailed data and research further from there. And there will be different stages of climb. The initial climb is going to go up to 17 degrees, and then it'll go up to 24, and eventually it'll go up to 30-degree latitude, which is fairly high. We'll be able to see quite a bit of the polar region. There will be 8 Venus flybys and 1 Earth flyby for this mission, and eventually the solar orbiter will be placed into an elliptical orbit that will be coming as close as 26 million miles from the sun. That will happen every 5 months or so.
Did you want to show your video that goes with this, or?
Yeah.
Right.
Yeah, let's take a look at that. I was going to show that in a minute, but this is the perfect time for it. So, as you can see, coming up, so this is the solar orbiter's journey around the sun. On the right, you'll be able to see the timeline. It'll list what day the flyby of Venus will be, and And it'll start with 2 flyby with Venus, and then it'll hit Earth once, and then toward the end, it'll be the remaining one will be with Venus. So there'll be a total of 8 flybys, like I said, and then 1 Earth flyby. And a total of orbits by the end of the mission, there will be 22 orbits toward the very end.
Yeah, this stuff is cool, right? This is like, I always say, like, math is the one way we have to really predict the future, right? Crystal balls don't really work, but, here we've predicted this entire thing for like the next, 10 years or so, right? All those orbital paths, and orbital intercepts, with math.
Yeah, so as you can see, after it fly by Venus for the 3rd time, by 2021, between 2021 and 2025, the angle inclination will tilt. And you can probably see that you pay close attention. You see a little tilt, and then you see another tilt, another tilt. After every few orbits, it will tilt a little more. And then as it goes through, when it comes to the closest point to the sun, it's going to really continuously capture data, a lot of data, as much as possible. So the spacecraft was built to carry 10 instruments, of which 6 of them are remote sensing instruments to measure what's happening far away at far distances. And then the other 4 instruments, they are made to measure conditions around the spacecraft itself. And then once scientists receive the data, the combine of the distances from far away and the ones surrounding, they'll be able to combine and make a lot of good conclusion, hopefully, out of it. And then, of course, we're going to get more news. We're going to be able to learn so much more from scientists. Okay? And then lastly, this is the image that's showing there's a green line, which is the spacecraft's orbital path. Okay? And then right there, that's where it is right now. You want to kind of
so
imagine
this is where it started, right? It started here, right?
Yeah.
And this was where, so it launched here, right? This is from the Earth, right? And then it comes around.
Correct.
And then,
it follows the green path.
Today we are like here. Or yesterday this was here, I guess.
Up
today
there.
we moved a little more.
Yeah. So just a little more. So just so you have a reference point, we have not made one full revolution. But we'll get there.
Yeah. Cool.
And for the folks that, if you didn't figure this out when you were watching the video, in addition to the orbiter's path, you actually had the inner planets in there as well. They're making their rounds, right? You had Mercury, Venus, and Earth. And in this image, you have Mercury, Venus, Earth, and Mars with the white orbits. And then, of course, the green path is of the orbiter.
And obviously, the sun is right in the smacking middle of it.
Yep, there it is.
So, so the spacecraft, it did go inside beyond the Venus orbit, of course, and then it could also go beyond the Mercury orbit also. It come very, very close to the sun. And at one point, it come as close as 26 million miles from the sun. And that happens every 5 months.
Very cool.
Okay? So again, there's so much more about this mission, and it's so new, and scientists continuously research and find out more about space weather. And that is essentially really protecting us, Earth. So if you're interested, please check out their websites to learn more, and I'll take questions toward the end. Thank you.
Okay, yeah, sounds good. Yeah, thanks. So I think this mission will probably give us news items for like the next decade, right? So this will be very cool. And this whole mission kind of reminds me of the New Horizons spacecraft that we sent towards Pluto a few years ago, right? Because we knew Pluto was there, we knew stuff about it, but as we got closer, and we're able to take close-up pictures, we learned so much more. And this is kind of the same way. It's like, wow, look at all the cool stuff, right, that we see when we can take a closer look. And that feeds nicely into our next topic, which Lipika will cover for us, predicting explosive solar flares.
Okay, thank you. So this is going to be about predicting solar flares on the sun. So like Wolf and Nancy talked about, some solar flares can get so powerful that they're actually detrimental to Earth and essentially us. So that's what we're going to talk about today. So trying to predict weather on the Earth, like we said, is already hard enough. when it's going to rain, when it's going to snow. It's already hard for our forecasts to determine that. So you can probably imagine how hard it might be to determine weather on the sun. And through the orbiter and things like that, we're able to get closer and research more. But still, it's quite difficult because we can't get it close enough proximity to it. So in this image, you're looking at a solar flare, which is from NASA's Solar Dynamics Observatory. They're the ones who captured this, and the solar flare is the one on the left. It's the blurb that's shooting out that's on the first one, basically. It's the light yellow colored one. Mm-hmm. So solar flares are very powerful bursts of charged particles and plasma. So if these solar flares, like I said, if they get big enough, they can cause something called coronal mass ejections, or CME for short. So it's really important. The reason why it's so important for us to recognize when these happen and just understand them is because, like I said before, they're very deadly, and they can essentially wipe out all satellite connections to Earth. So all the technology and all the internet that we're using, we won't have access to it. So the reason we want to predict these, and the reason it'd be good to predict this, is so we can kind of prepare before it happens. There are ways that you can blockade, and basically you can recover satellite information. There's lots of things that you can do so you can stop the effect from being that big. So that brings me to the research topic. So a group of research physicists in Japan, they're trying to figure out ways to predict solar flares. So currently, they've predicted whether or not solar flares will occur, where they're going to occur on the sun, but most importantly, how powerful the solar flares will actually be. So in the next image, this image is showing you a large solar flare that erupted on September 10th, 2017. And the kind of grayscaled area background is the ultraviolet view from, again, NASA's Solar Dynamics Observatory. And then the red blurbs that you're looking, the three red blurbs, you see that there's a variation of red to blue within the middle one, and that's showing increasing microwave frequencies. And so, yeah, the other two don't have blue, but there is some orange and red, so that's still a increase of red to orange. So in their technique that the scientists use, they use magnetic field lines, which is everything that the lines that are coming out of the sun. And what they do with these field lines, they use a computer model, and they kind of overlay this magnetic field over a spot with sunspots. So the article did not specify where the sunspots were, but they can either be where those red blurbs are shooting out, or the edge of the sun. The edge of the sun that we can see. Also, for reference, the sun is the thing that is closest to our image. The circle. Mm-hmm. So basically, the reason they're overlaying the magnetic field lines is if you look at the twist that's coming out from the furthest red blurb to the one that is nearest to us, that's that amount of twists that the magnetic field is generating in the computer model, and overlaying that with the actual magnetic field from the sun. That's what we're trying to see, the change of the site. And so this change is called a reconnection event. So in the next video, we're going to look at what magnetic reconnection is. So just to give you a little bit of context, a magnetic reconnection occurs when magnetic field lines are close and they're roughly parallel to each other. And this event happens when they merge. So the energy that's released from this connection is kind of like when you have knotted rubber bands and you snap them together. There's this huge there's a lot of energy that releases when the snap happens. So if you look at this video, this is what it looks like.
Yeah, so these are really powerful events, or they can be very, very powerful, right? So they come in all varieties here, and it's fun to see the modeling, or in this case, I guess it's an actual recording of the magnetic activity here. Right? You can kind of see how the magnetic fields form and then separate, and it's this abrupt reorganization is what triggers the solar flare with a strong emission of radiation and particles.
Just to kind of reiterate, the reason why all this is important is so we can take preventative measures, and in order to save us, essentially. So it's really important to predict when these will happen. So it's better for the Earth and us.
Absolutely. Yep. Okay. Very cool. Thank you, Deepika. Okay.
And one other thing to add there is these reconnection events and also the campfires that Nancy talked about are also part and parcel of why the corona happens to be a lot hotter than the surface. So they're adding, that energy is actually adding to the corona and making it so much hotter.
Yeah, that's actually something we didn't talk about so much, before we got to this point. But as a really quick aside, of course, the core of the sun is where the energy is produced. That's super hot, and then things actually get kind of cooler as we go to the outer layers of the sun, like to the photosphere and corona, the chromosphere, excuse me. But then, the outer corona turns out to be super hot again, right? And it's like, well, why is that? And so that's an interesting thing that scientists are still working on. And one possible explanation here is that these magnetic events, right? They are transferring energy to the corona. Okay, let's see. Let's take another quick look at the backyard, because in a moment the sun will disappear behind a tree. So before it does that, we'll visit back there one more time, and then we'll wrap up with a final topic from Emery. Let's see. All right. So here we are again in the backyard. Let me position the telescope a little bit. I hate it when I hit the wrong button. It goes the wrong way. Okay, so we still have this prominence here, and it's probably getting a little harder to see, maybe because of just the atmospheric effects, but still there. And every time I have this dark dot here, and every time I think I need to find this and clean it, and I always forget. So this dot over here is not a feature on the sun. That is dirt somewhere in my telescope. Yeah, things I guess haven't changed appreciably from when we looked at it a moment ago. But again, you can see the nice orange skin texture in the disk of the sun, right? I think that's cool. And we still have this prominence going on down here. Although I think it was a little more pronounced, I think, when took these pictures earlier in the day. Okay. So you guys can all cross your fingers that maybe the current solar minimum will come to an end soon, and then we should be able to see a lot more exciting features on the sun with our H-alpha equipment. So that's something.
As long as a lot of the energy is not directed towards us.
Correct. Yes. So any of those big kablooies that could be happening up there, we prefer that go somewhere else, not towards our homes. So.
Laurie does have a question. Is the magnetic field of the sun different than ours due to the liquid swirling equator?
I guess maybe the question is, what would you mean by different? I mean, I think it's different in terms of its arrangement and structure. The magnetism is the same physical phenomenon that we experience here on Earth with our own field, but the fields are just way more complex and much more variable. Right? Whereas our Earth's magnetic field is pretty stable. It actually moves around too, but it's really pretty stable. The sun's fields are all over the place all the time, like those messy pictures I showed earlier. If you were here during the first part, I showed those magnetic field pictures that were like morning hair, especially if you haven't had a haircut for several weeks due to the pandemic.
Cool.
Okay.
Thanks, Wolf.
Sure. Okay, let's switch back, I guess, and we'll have Emery wrap up for us here with interstellar mapping and acceleration probe, the IMAP mission.
All right, thanks, Wolf. So, hey there. So, like Liptica's topic, this will also be about emissions from the sun, but where Liptica discussed solar flares, I'll be examining some different emissions from the sun, like the solar wind magnetic field. So, the focus of today is a new paper published by the Princeton University's Astrophysics Department. More importantly, you can see a paper on the left side of the screen. It's about the IMAP probe, the Interstellar Mapping and Acceleration Probe, planned for launch by NASA in 2024, which you can see as an example in the bottom right of the screen. So with 10 highly complex instruments and positioned at the Sun Earth L1 point, which is the kind of left of the Earth, as you can see in that image. Yep, Wolf. It's going to be able to examine all the way to the outer edges of the solar system, and it's going to be trying to examine 3 different types of phenomena to satisfy the goals of its program, and we'll be going over exactly what these goals are. So next slide. Yeah. The first of these objectives is to study the interaction between the sun's magnetic field and the local interstellar medium. So what does this mean? Wolf already discussed the sun's magnetic field, but to quickly summarize, it's thanks to the complex mixing of charged particles in the sun, a massive system-spanning magnetic field is produced. So just as we talked about, the Earth's magnetic field is very stable, but very confined, whereas the sun's is much, much more powerful, and we can see kind of the effects it can have here near these outer edges of the solar system. So it serves a number of purposes, but one critical role it plays actually is protecting us from galactic cosmic rays. So you know how the Earth's magnetic field kind of protects us from kind of the emissions from sun. Similarly, these galactic cosmic rays, which are basically subatomic particles, accelerate to almost like light speeds by distant supernova explosions. So very, very dangerous stuff. The sun's magnetic field, similarly to our magnetic field, is able to deflect particles and protects us from a majority of them. And so what we want to see is that how it does this process. So these particles can be highly deadly to our astronauts and satellites that we have in space. But thankfully the sun's there, and so we want to understand this process. And so with the IMAP probe, we'll be able to examine this far out in the system, kind of understand this region, which is the heliosphere, which you can see is the kind of that separation between the termination shock and the heliopause. So it's that nice, bright, flaring surface. So it stretches back behind the solar system as well. And so we will just further study this and better understand this process of deflection, and kind of through this better understand exactly how the radiation composition of our inner solar system was able to develop thanks to this deflection from the sun's magnetic field. The second goal of the program, so this is a big part, but it's also related to the heliosphere, and that's discussing the interaction between the solar wind of the sun and the local interstellar medium. So same area, however, different emission from the sun. So again, the solar wind is a continuous flow of particles from the sun. So where solar flares are kind of explosive releases of energy, this is kind of like continuous emission. And that's what's interesting about these solar winds at these outer bounds of the solar system is that we find that the solar winds made up of protons, most importantly, hydrogen atoms. And when they go this far out in the solar system, they begin gaining and losing electrons repeatedly. And if they do in the right place at the right time, they can actually be emitted back into the solar system. And so some NASA missions before, such as the IBEX program, which isn't terribly relevant, it's a satellite similarly. However, they recently discovered this. However, they don't have the capabilities to really further pursue the topic of how this process occurs. And with this 10 array number of instruments the IMAP probe can carry, they'll be able to examine this process similar to the sun's magnetic field and that interaction, kind of bringing light to under-research field that scientists are really interested in. And the final goal of the program would be to study the particles being emitted by the sun. So these particles are of particular interest because they can, again, similar to galactic cosmic rays, endanger astronauts and satellite equipment we have. But with this high importance, scientists are obviously eager to study the emission of these particles in depth. And for this IMAP probe carries specialized equipment to help us understand exactly how these particles originate from the sun. It's not exactly contributing to a novel field like the local interstellar medium with the sun's magnetic field and the solar wind. However, it's a welcome addition to the current equipment already out there, and the scientific community greatly appreciates the further opportunity for research. So that's pretty much it. So the IMAP probe, it's pretty exciting, and overall, it's going to be exploring the heavily under-researched fields of the interaction between the local interstellar medium and the sun's magnetic field and solar wind, along with providing useful information for particles being emitted by the sun in these solar winds. Overall, it's a very promising new tool for future heliophysics research, which could be, wouldn't be surprised if ends up getting some really cool discoveries about these interesting interactions that we have in the outer bounds of the solar system. Yep, that's pretty much it.
Cool. When do we expect to start getting data on this then? When will we expect results from this?
It's planned to be launched in 2024. However, I mean, NASA, it's kind of be postponed a lot. The James Webb Telescope is a famous example of that. But I think there's around like a couple month testing phase. But I would guess, based off just past experience, like 2026 is going to be really, really, really kind of getting all that data that it needs, and kind of getting after that period of some data collecting, we begin to get some really cool discoveries thanks to this probe.
Yeah, astronomy is not a good science for the impatient, right? Because even with Nancy's story, right, we launched the probe, and it's a 10-year mission, right? And it takes a long time for the probe to do all its orbits and do the flybys of the sun. So yeah, if you're impatient, this is not a good science for you. On the other hand, with that patience, we often get a good payoff, right? Like huge new detail about the campfires, for example, right? And I'm sure there are things that we have not even seen yet that, the solar orbiter that Nancy talked about, and then this mission here, IMAP, right, will reveal. So this is really cool. That'll be cool stuff to look forward to. All right, thanks, Emery.
Yeah, I mean, in simple terms, I think, Emery, what you also talked about is all that solar wind and that energy sort of creating this electromagnetic force field, right, and the outer limits of our solar system that's protecting us. And then these missions are pretty much, to find out the inner workings of how a lot of this energy, how it's going out, how it's hitting the boundaries, what is it protecting us from, protecting, for future protection for our astronauts and our equipment, and additional research that'll come with it as we start looking at increasing our boundaries once we get to Mars and we get further on. I mean, there's so much more that human race is going to accomplish. So all this science is going to feed into it.
Exactly. One interesting thing I didn't mention was with this research about the heliosphere, they'll be able to actually better understand its composition. And so actually the Voyager 1 and 2 probes are just now beginning to enter this area. And so we're better able to understand how these areas are kind of constructed, then we can perhaps kind of better understand how the Voyager probes will fare in these areas, and perhaps protect them and continue our mission on.
Right. And the Voyager probes, just for context, right, these are spacecraft we launched in the 60s, I guess, right? I forgot the exact years now. Yeah. But yeah, so again, this is not for the impatient, right? We launched the Voyager probes, 60 years ago. And, they did a great job exploring the planets way back when, but they've been traveling towards the, outside, right? Away from the sun since then. And they're now finally, recently, I think one or maybe both have just crossed that boundary of the heliopositive solar system, but they're right in that neighborhood. Yeah.
Yeah. Voyager 1 launch date was September 5th, 1977.
77, sorry. Thank you. Okay. See, bad updates. Thanks for rescuing me here.
And Voyager 2 was also 1977, but that was August 20th.
Cool. Yep. Thank you. All right. Very good. Thank you. So, final view from the backyard. So I think, like I said earlier, we run into the tree. So there it is. So now you get to see the sun as it's either obscured by a giant alien spacecraft, right, or by leaves from my tree. You can guess which one is more likely. But okay, I think that pretty much wraps up our chat today. So I really appreciate everybody's participation. Are there any final questions? Is there anything in the chat that people have thrown at us that we should address?
I can help you with the solar view.
Oh, thank you. Yep. Okay. Can you please demonstrate differential rotation? Thank you. Okay, looks like there are no final questions as far as I can tell. Okay.
No questions.
All right. Okay, well then we'll wrap it up for today. So just a reminder, we're the San Jose Astronomical Association. We do lots of stuff, not just the solar events. For example, next weekend we will have a science talk. Actually, Emery is the presenter, so Emery will speak about binary stars next Saturday evening. And then the following weekend, on the Friday the 14th, I'm doing a general introduction to astronomy I call Sights of the Cosmos. And then the Saturday, the 15th, we have an armchair star party. That's our online version of a nighttime star party, and that's quite a production, so go check that out. All these things are listed on Meetup. And again, if you like what we do and you'd like to become a bigger part, consider spending that pizza money on SJ membership. And also, if you're interested in helping out and learning and promoting astronomy and science in general, we can use your help. In fact, that's how Lipika and Emery got here, for example, right? So we can use help in technical and non-technical areas. Don't worry if you don't feel ready. We can help you get going. Just contact us, ask SJ, which is a general account, or you can reach me at Solar. And say hi. And if you want to work with SJ to do what we do, that would be awesome. And with that, I'm just curious if you want to give us some feedback in the chat. I'd be curious to find out if you found anything in particular most interesting or most surprising. Do tell me about that. And in general, if you just have feedback about how we can do better, I'd appreciate it. So thanks. Thanks for visiting. That's Streaming Solar Sunday for today. I appreciate your time with us. And have a good rest of a Sunday. Bye, everybody.